We're done with chapter 6, and now we're going to chapter 7. And chapter 7 is an interesting chapter. It's all about waveguides. How many have heard the term and know what a waveguide is? Well, you know what a transmission line is, right? Coax cable. I want to just tell you the big difference between a waveguide and a coax cable. When you have a coaxial cable, or really a transmission line, but you have something, and really, the cross-sectional area has to be the same, but it doesn't matter if it's circular. Like here we have, I'm going to show you the cross-section of a standard circular transmission or circular coaxial cable. This could be grounded. This would be the plus potential. There'd be an inner and outer radius, and the thing is long, and it has a constant cross-section. Now, with this, or I mean, for a transmission line, you could just assume, just as well have this, and this is what happens with a lot of microelectronic circuits. You simply have a dielectric layer here, and on top of it, you'll have a piece of copper, and you'll charge this plus and have this grounded. So the electric field lines look like this, if you were to plot them and trace the electric field lines. Here, the electric field lines are radially out. And I think you all know that, right? Now, the magnetic field lines for this one would be circles. They'd be concentric with the inner core. And for both of these, there would be no electric or magnetic field in the direction of propagation. Do y'all follow me on that? I mean, yes, there is an electric field. It's a very, very small electric field that's pushing the current down the inner conductor and back, but that is very small, and it's not a propagating current either. The electric magnetic, well, it is and it isn't. The field propagates because it's contained between the inner and outer conductor, and it moves that way. But basically, I think you know what a T-line is, right? Now, a waveguide's different. By the way, transmission lines they work at DC on up. They work from DC on up. Waveguide is different. Waveguide has electromagnetic energy that's confined and bouncing down there. Here you have a plus to minus voltage and currents that are driving there. But when you have a waveguide, here's what you really have. You have a hollow pipe. This is our conducting waveguides. So you're going to have some dimension here, A, and some dimension here, B. I'm going to call this the x-axis. Call this the y-axis. Now, actually, if you look at this x cross y, this would be the z-axis in this direction. And there would be propagation, but this way. But if you can imagine just a rectangular pipe that's conducting. So this wall here and this wall here are conductors. What this does is confine electromagnetic energy. So it's moving and it's bouncing or ricocheting up and down the guide. Y'all follow me on that? Now, if you think about that, just think about the floor being a good conductor and a constant altitude here being just a perfect conductor, and having an electromagnetic field of polarization in this direction. When it hits there, it reflects off like this, reflects off like this. Y'all with me? And that's what's sort of happening. It's ricocheting down there. If I just looked at the cross section, you have to appreciate the physics to really understand these, in my opinion. So you have really an electromagnetic wave that's going like this, striking that, coming like this, striking it, coming like this, and striking it. And there's a condition though. The tangent electric field here has to be zero. Do y'all follow me? If that's a good conductor, we know E tan is zero on a good conductor, right? It shorts it out. So if the electric field's in this direction coming out of the board, Then when it hits here, it would go to 0. All right, this would be the electric field coming out of the board. It would have some relative max, but when it hits here, it would go to 0 again. And the same way, you all follow me on that. Now, if the electric field is in this direction, it could still have a component in the direction of propagation, right? Depending on how it's bouncing, but it could have a component along that direction. But that the component that's or in the direction of propagation would have to go to 0 here and here. Does that make sense, Steve? You're really, with waveguides, the thing that they talk about oftentimes is, assume you have an electromagnetic field in this direction, and you're going to have an identical field in every way, shape, or form, propagating this way. So it's a mirror image. It's what's propagating up here. And this one would be propagating like this. Now, the thing about it is, if you can do this, it's called the summation of 2 plane waves that have the same, you might say, tilt angle, same polarization. You can do that so that the boundary conditions at these edges are 0, and that does solve the problem. I'm going to do it in terms of a solution of Maxwell's equations. This is the exact way, it's the way engineers do business. They don't talk in generalities and say, oh, well, that's it. We actually solve the equation. But I want to tell you, a waveguide really is some conducting pipe that confines electromagnetic energy. It just bounces along. All right, that's all it is. And the difference between a transmission line and a waveguide is, a waveguide is really a high-pass filter. You have to get a frequency above which things propagate. Here's why. When you look at the top and bottom, and I can't get there with you right now, but I think you'll appreciate this. You know, you're going to have electromagnetic waves flowing. They're basically going to have a wavelength, right? I mean, they have to. Well, if you think about that, there is a cutoff frequency at which below that frequency, it won't propagate. What I mean is, there's a cutoff wavelength. If you take a look at A, if A is greater than B, all right, when you get a half wavelength in this direction, anything that would try to be bigger, right, won't work, because the electric field, I'm trying to show you that being the envelope of the electric field in the vertical direction there, it won't go to 0. Do you follow me on that? So that's sort of physically, I'm trying to give you a little bit of an interpretation of why these things are high-pass filters. Here's a physical analogy to it. You know that you can get echoes and caves and things like this, but if you take pipe, you all know the pipe has a natural resonance. Like blow over a bottle, you hear, right? Well, the narrower the pipe, the higher the resonant frequency. But also, what happens is if you have a long pipe, you have to go above a certain frequency before stuff propagates down that pipe, before you can actually get waves down there. Otherwise, they just attenuate super fast. You just have to appreciate that. Same way here. So now with waveguides, I'm going to go ahead and start by solving the equations, the electromagnetic equations for these waveguides or hollow pipes. And this is in chapter 7. I want to do this in a way that if I was sitting where you were, I would want it done for me. So as engineers and physicists, we always start with the fundamentals. Start with the things the laws that are never broken. And those are Maxwell's equations. So we take the curl of E, and we say, and we're going to do this in the phasor domain. Is equal to, and this would be minus j omega mu times h. And let me just draw my waveguide here. This is going to be the cross section of the guide. It's infinitely long for our purposes. This is going to be x. This is going to be y, and coming this way is z. And these are going to be perfect conducting. This is a perfect conducting pipe right here. So this dimension will be A, the horizontal dimension, and the vertical dimension B. This is consistent with Dr. Wentworth's, all his discussions in chapter 7. Anyway, equations that directly apply that start off with curl of E is equal to minus J omega UH. That's Michael Faraday's law of induction. I didn't put it in the time domain form, and I already replaced B with mu H. We've done that for plane waves, if you remember. Next is, we'll take max. We're going to also assume something that in the center of the guide where the thing's bouncing, sigma is 0. All right, you just write that down. It doesn't have any loss. If it did, we wouldn't be talking about this because you're not transmitting things down, lossy stuff, right? We're assuming sigma 0 or its lossless. So then we get the curl of H is equal to, normally it's sigma E, but since sigma 0s, we ignore that, just J omega epsilon E, right? Out of curiosity, do you remember what law this is? This is Michael Faraday's law of induction. Do you remember the scientist we credit with this? Ampere. Faraday's law of induction, Ampere's current law, or circuit law. Now those two equations always work. We're in the phasor domain. We're assuming we're at a constant frequency. And generally speaking, when you talk about waveguides, you do talk about constant frequency, or at least the narrow band of frequencies. Now, we always want one equation with one unknown. When we talk about solving electromagnetic phenomena, we need the solution to one variable. We can't juggle. I mean, we can't have an E and an H where one depends on the other in terms of unknowns. They have to be one equation with one unknown to solve it. And that's true of differential equation theory, if you remember. We always went that way. So I'm going to take a second curl of the first one. So I have curl of E, and that's equal to minus J omega mu times curl of H. Again, we've done this before. Do you remember my next step? I want one equation with E. Anybody? How do I get one equation with only E? Take a look there. Well, I used the first one, right? What about the second? Don't I have a curl H in the second, and I can replace it with that, can't I? Sure. So I'm going to just say this is equal to minus J omega mu, and then curl H would be J omega epsilon E, right? Now, if you look, I got one equation with just E. Take a look at the first and last term there. You all see it? Okay? I'm going to go ahead and do something here. The curl of E, if you remember from the wave equation and how I simplified, I said that was equal to the gradient of the divergence of E, right, minus del squared of E. And that was equal to, well, here I got J times J is minus 1 over the minus is plus 1 is equal to omega squared mu epsilon E. Are you with me on this? You remember when I did that before? All right. Now, there was another assumption I made at this point before for the free space waves. Does anybody remember what it was? Well, what about the divergence of E? What is that usually? Anybody? Why though? What is divergence of D? Let's try that. Do you remember what divergence of D is? You're going to need to know this. By definition, isn't that the volume charge density? And what law is this? It's the point form or differential form of Gauss's law. Sure, because we know the integral of the charge inside a region is equal to the flux penetrating the surface around it, right? So the integral of E dot ds is Q inside. So this is the point form of the differential form of Gauss's law. We assume this is 0. That means there's no free charge inside the guide. Not on the, not on the edges. There's basically it's a vacuum. You can assume that for now. It's not really true, but so when we do this, if divergence of D is 0, right? It also means divergence of E is 0 because we know rho v, we know E is epsilon, or D is epsilon in, right? Are you with me on this? So if D is epsilon E, you would get divergence of epsilon E equals 0. And assuming epsilon is not something that spatially varies, then it would be 1 over epsilon, or divergence of E is 0. Okay, everyone? All right, that means this one goes away, and I have that. So now I have del squared of E, right? And if I take this to the other side, it would be plus omega squared mu epsilon E is equal to 0. That's true inside the guide. This equation right here is inside the waveguide. Now, here's where we have to make some assumptions. Remember, with plane waves, we made assumptions. We assumed one overwhelming fact. We assumed the electric field had only one polarization and it only varied in one direction. Do you all remember that? Right? Here, we're going to assume only one polarization, but it's going to vary in both zx and y because that wave is going to be bouncing. Do you all follow me on that? So it is going to have variance in more than one direction. Now, in general, we have E equals some EX AX plus some EY AY plus some EZ AZ. And the same thing would go for H. You would also have an H in general that would be equal to HX AX plus HY AY plus HZ AZ. All right, so there's really three field components to both E and H, right? In general. What we're going to do is say this. In order to do this thing and make it doable, we're going to try to get these things down into some reasonable forms to solve. So, and this is borne out with measurements and theory and everything like that. So the first assumption we make, write this down, this is going to be transverse magnetic. We're going to assume a transverse magnetic, or TM wave. All right, now you all remember what TM meant when we talked about TE and TM with electromagnetic fields striking regions, right? If it was TE, the E field was out of the plane it was traveling in, right? Or the E field was parallel to the surface. Do you all remember that? And if it was TM, it means the magnetic field was sticking out, right? Do y'all remember that? Now, for TM inside a waveguide, we could do the little exercise with the wave striking that, but the easy way to do it is if it's TM, the magnetic field in the Z direction is 0. So there is no field in the Z direction. That's if it's a TM wave. It means this. Remember, think about it. This thing's really bouncing this way, isn't it? It's bouncing like that. Mm-hmm. So transverse magnetic means the magnetic field is perpendicular and in the direction of propagation, or down that z-axis at 0, because it's slamming into the lower and upper, boundaries. So this is a TM field with respect to the boundaries. Do you follow me on that? The conducting boundaries. That means it only has an EZ field in the direction Z. Now, the nice thing is, when I do this del squared operator, I'm just going to, you don't need to write this down, just listen. The del squared operator of a vector, and this would be in Cartesian coordinates, so it's different in cylindrical and spherical, would be del squared. That's the second derivative of the x, second derivative of y, plus second derivative of z, of E x ax plus, and then it would be a second derivative of, now it'd be the y component, a y plus the del squared operator of EZ az, because E has both x, y, and z. Well, there's 3 derivatives that operate on EX, 3 on EY, and 3 on EZ. That means 9 derivatives, second order derivatives with respect to EX, EY, and EZ would be there. It's a mess. Right? We don't do that. We assume the only thing we care about, because these are vectors, so this does not directly affect that technically when we solve the differential equations. We're just going to look at the EZ component, the del squared, and I should say of EX, sorry, del squared of EZ. I'm sorry. I'll get there. Let me give myself some more board because I'm already thinking ahead of how I'm going to go through all this. I'm trying to do this in a way that would be as meaningful as possible without overloading you with some of the details. So here's what happens, and this is consistent with Dr. Wentworth's book. Remember, we're in that pipe, and now I go ahead and I have del squared of EZ right here. We're only talking about the EZ component. And this is for the TM mode. All right. Then it's going to be plus omega squared mu epsilon EZ equals 0. The only one we're going to look at. HZ is 0. Right? So for this, we've got this equation. So how do we solve it? Well, we'll start by creating a constant. I'm going to say beta squared is just equal to omega squared mu epsilon. That takes care of rewriting that over and over again. You all follow me that? Because that omega squared mu epsilon, I have to write over and over again. That's beta squared, isn't it? Beta is just omega squared of mu epsilon. So that's the first thing. The next thing I'm going to do is use something that you remember from math, probably your mathematics courses, separation of variables. All right. Do you remember that term, separation of variables, or any of the differential equations? We did this by we're saying we're going to assume a solution. We're going to assume EZ. We're going to see if this works. If it doesn't, it doesn't. It's just a function of X only times a function of Y only times a function of Z only. In other words, it could be a cosine of beta X, sine of beta Y, e to the j beta z. All right, in other words, we don't know, but it's a function of just X, Y, and Z. And if separation of variables works, then I'll be able to get functions just of X, just of Y, and just of Z equal to each other. And I don't know, do you remember, how many remember separation of variables? You were nodding your head before. Yeah, and it's extremely powerful. In engineering, you're going to use this. If you get that, depends what you're doing, but I tell you, a lot of times when you're dealing with the fundamental equations that govern things, you start with differential equations. When you get down to a differential equation and you want to see a family solution of solutions, you'll use separation of variables in both space and time. And you'll get 2 sets of equations that'll mate to each other, but it becomes extremely powerful. It's a technique. If not as powerful or more powerful than like Laplace transforms for solving just standard one-dimensional Diffie cubes. Okay, so come down here and I stick this solution in here. So my del squared E then becomes, and I should put this down here one time, del squared of E in EZ would be equal to the second derivative of EZ with respect to X squared plus the second derivative of EZ with respect to Y squared plus the second derivative of EZ with respect to Z squared. That's what del squared EZ is, and then I'm going to add on this term right here too. So then I'm going to add this plus beta squared times EZ equals 0. Now y'all realize I just took this equation and I broke this thing out into its definition. Y'all follow me? Everybody follows me? Now I'm going to go ahead and I'm going to use the separation of variable technique. If you haven't had it, it's time to pay attention. You got to watch this. So here, That's a function of only x, function of only y, function of only z. Go with me? When I take two derivatives of this with respect to x, it's just x double prime. That's the way we indicate it. You with me on this? One derivative be a single prime. Double prime is two derivatives. So here I have x double prime yz plus, and then it would be x y double prime z plus, then it would be x y z double prime, because that's going to be with respect to z, plus beta squared x, y, and z equals 0. This is in his book, but just realize what I'm doing. I'm just executing the derivatives on that and indicating derivatives by the prime. You all remember primes from your math courses, right? They usually had it for time, you had primes, but you can use it for anything. Now when I get down to here, I'm going to divide everything by the functional form of x, y, and z. I don't know what they are yet, but I'm going to divide by this, x, y, and z. And when I do that, I get x double prime, all right, the yz's cancel, plus y double prime, the xz's cancel, plus z double prime, all right, plus beta squared equal 0. And here, again, I divided everything by this function. With me, guys? If this seems like it's going nowhere, trust me, it's coming together now. I'm going to make this point. Now, this function of x, right, and I'm sorry, this is divided by x. That's the functional form of x. Divided by the functional form of y, divided by the functional form of z, right there. But remember, I divided everything by x, y, and z, so it's gone from there, but I still have a z I have to leave here. I still have a y that I have to have here and an x that I have to have here. You all with me? And remember, x is a function only of x, but we don't know what it is yet. Now, I can make this argument to engineers without going through a formal math proof. If I have a function that's only of x, right, plus a function that's only of y, equal to some constant k, and that's what this is saying to me, then f of x has to be a constant. Do y'all follow me? If it's not, then for any value of y, that would, let me put it to you this way. If f of x or f of y varies, if I freeze one and change the other, this wouldn't be true. Y'all follow me on that? So because of that, I can say that x double prime over x is really a constant. The constant we use is minus, and the reason the minus sign there is it makes the math easier, just minus beta x squared. The constant of y double prime over y is minus beta y squared. And the constant of z double prime over z is going to be minus beta z squared plus beta squared equals 0. And here again, I'll just put the 1 down. X double prime over x is equal to minus beta x squared. Some of you probably are guessing that has to do with the propagation constant in that direction, and you are right. You remember when I broke k down to k sub x, k sub y, k sub z? This is the same deal here. I'm using beta because his book uses beta. One other thing Dr. Wentworth's book does that I don't particularly like, so I'm not going to do it, is instead of beta there, what Dr. Wentworth's book does, and write this down, he uses beta unguided to be omega times square root of mu epsilon. All right, so I'm going to put his definition here now, even though I don't like that. And then beta that he uses is beta z. I'm going to leave beta z alone because it's important that you have a feel for that. That beta has to do with the z direction propagation period, because that's the way this wave is going to be propagated. So that's the equation, okay? We're still not done yet. Now I'm going to have to redraw the actual the waveguide. Do it right here. I'm only going to show you cross section. This is going to be the A dimension, and that's a little tall. I'm going to show you some things, and this is going to be the B dimension. And A is less than B. I can tell you how much less in a bit and why. So when I do this, and I didn't put this down here, but this is going to be the x-axis, and this is the y-axis. And that's really representing the cross-section of the guide. Y'all follow me? So I took a rectangular, like think of like a ductwork or something. All right, you just cut it in half and look down. Now, when I have this equation, what this necessarily means is this right there is the constant equals that, so I'm going to solve it. So I have x double prime over x is equal to minus beta x squared. And if I go ahead and multiply both sides by x and then solve and get one equation, I get the second derivative of the variable of the variance with respect to x squared plus beta x squared x is 0. Do y'all follow me? I've just rearranged things, make my life easy. Now, that's the standard second order homogeneous differential equation. We could solve this. We could get us doing the assumed solution. We could take the Laplace transform. Instead of time, we'd have space. It doesn't matter how we solve it. No matter what, when Dr. Wentworth spoke, he just used the assumed solution and then find the constants. X here can be either have a variation as cosine of beta x times x, or it can be a sine of beta x times x, or it can be e to the plus or minus j beta x times x. Now you try, the reason I'm saying it can be plug a cosine first. If this is a cosine, if x is a cosine variation, two derivatives brings out a minus beta x in front of there squared times cosine. So you would have minus beta x squared cosine, then beta x squared cosine equals 0, checks that box. You follow me? Same with the sine. Two derivatives on sine and voila. That equation solved. Same here, because if you take out either plus or minus j, whichever one, bring that thing out in front twice, because each derivative will bring out the minus beta, j beta x. You get a minus beta squared, beta x squared, and it would be here. And in other words, these are the possible solutions. Do y'all follow me? We got to find the one that works, and here's how you do it. Remember I said that EZ was multiplied by this times this times this, right? Now, at the boundaries, this has to be 0. Do y'all agree with me? EZ is in the direction of propagation, right? So it's going down the guide, and we know anything that hits these edges, the tangent component is 0. So EZ has to be 0 here, right? If you think of EZ, it's actually pointing in, right? It has to go to 0 there, right? And it has to go to 0 there, doesn't it, class? Mm-hmm. You might not be seeing this, but remember, this is a variation x. So if you think right in the center of the guide, as you're moving this way, you can have EZ in this direction. But whenever you come to this edge, it's got to short out. Do y'all follow me on that? And the only thing that'll work, if you look at this, if you have a cosine, because this is x equals 0 here, if you have a cosine of 0, it's 0, right? No, cosine of 0 is 1, isn't it? So when x is 1 here, regardless of the value of beta x, the cosine is 1, right? And if the E field varied as a cosine, it wouldn't go to 0 right here. But the sine would, wouldn't it? And likewise, this plus or minus j beta x times x, that always has a magnitude of 1. The phase changes. So because of this, the x solution will vary, or will be some constant. I'm just going to call it E naught, and it will be times the sine. Remember this, sine of beta x times x. That's what it's going to be. It'll vary as a sine versus x. We don't know what beta x is, but that's going to vary as a sine. Now, how do we get the value of beta x? Remember, this is how it varies with x. This is the z component. Well, I know here, when x is right here, it's 0. The sine is 0, checks that box. Where else is this got to be 0? Right here, right? Because EZ is going in, right? It's in that direction. It has to be 0 at this edge when x is equal to 8. You all see that? Remember, I'm trying to use this marker to indicate EZ. It doesn't matter what y is, but in the center, at least you can see that as it hits this edge, it has to go to 0. So what do you know? That at that edge, the sine of beta x times, well, what's the length there? The horizontal dimension. Can you all read that? A, right? So beta x times a has to be 0. All right, what arguments of sine are 0? Well, when the argument of sine x is 0, it's 0, right? What's the next 0? Pi, isn't it? Right? So one thing I can do, and this works, I can say that beta x times a is equal to pi. Now, it's also 0 for what? 2 pi, 3 pi, m pi, right? So I can say, therefore, that beta x will be equal to m pi, and m is just an arbitrary integer value. It can be any integer, but it's an arbitrary one. And then I divide by a. So lo and behold, I have my value for beta x. And now I'm going to create the solution right here. I'm going to say that my EZ is equal to some E naught. First one is going to be the sine of m pi over a times x. Now we've got 2 others to go. We do the same thing for the y variation. Y'all follow me on this? Now I'm going to just use this and erase x here and replace it by y. Well, I'm going to erase this whole thing. So now, come down here. You can see what's going on here. Now, I go to this guy. That's equal to, I have y double prime over y equals minus, and this would be beta y squared, right? Like before, multiply both sides by y, right? And then get one equation. So I have the second derivative of y with respect to, here it's going to be plus, that's second derivative, plus beta y squared times y equals 0. And again, that y is proportional to the electric field in the z direction. And you know it has to be 0. If you think about the electric field in the z direction, anywhere on this outer boundary, it has to be 0, right? Now at y equals 0, it has to be 0, no matter the value of x. Do y'all follow me? And at y equals b, it has to be 0, just like the other one. You with me on that? It has to be. And because of that, it means the y variation has to be a sine. I'm just going to put the values in here. So y will be equal to some constant. And I can just put some E naught, some unknown. And it will be times the sine of beta y times y. It will be that. It can't be a cosine, can't be an exponential. They'll never go to 0 and y 0. That's the reason. And we get beta y by doing what? We know the sine, right, of beta y times the height, b, is equal to 0, right? Well, the argument's the sign that makes sine 0. I went through this as 0. That box is checked already. And it's for all values of b, right? We know that would be for an integer value times pi. And I'm going to use n here. So that means beta y is actually equal to n pi over b. I've done the division already. And over here, because I'm trying to get through this before your quiz, this is going to have a sine of n pi over b times y. Let me erase this. Then, after that, still got one more, got the z variation. Now here's the thing with the z variation. It's going to have the same form as that. Right? The differential equation is going to be the same form, but the solution is going to not be that, because here we've got something else going on. So now when I take z double prime over z is equal to minus beta z squared, and I'm looking for the solutions, I get z double, or the second derivative of z with respect to z squared, right there, plus beta sub z squared times z equal to 0. For this one, now just listen to me, this is the z variation. I've already taken care of the boundary conditions at x and y is 0, at x equal a, and at y equal b, right? Now the z variation, I know there are no natural zeros. That thing propagates forever. Are you with me? And because of that, it eliminates the sine and cosine, and it comes down to this solution. Once you take a look at this, z will be of the form e to the plus or minus j beta z times z. It'll have an exponential sense to it, and that's propagation. So then multiply this by e to the minus j beta z times z. Okay? I know this stuff to appreciate this, you have to view it from my position. You have to use it a lot. You have to be, it's got to do something for you. Right? We're about to see it do something. So I have all this information. Right? I found out what beta x was, found out what beta y was, find out what beta z was, right? Now, if you remember, I had minus beta x minus beta y. There's got to be a way to prevent that. But I'm not going to mess with it. Finally, minus beta z squared, and then it's going to be plus beta unguided squared, right, equals 0. Now, I know what beta unguided is. That's omega squared square root of mu epsilon. I know what beta x, beta y are in terms of m pi over the dimensions a and b. And I know what beta z is. Kind of. I don't really. I need to find beta z. Do y'all follow me on this? That's what we do next. So I can say that beta z, and just follow me on this. I'm going to take beta z to the other side. So I've got beta unguided squared here, which is really, I'm going to write it down as omega squared mu epsilon. That's beta unguided. And then it's going to be minus beta x, and beta x is going to be m pi over a squared minus beta y, which is n pi over b squared. And that, well, and then I got to take the square root of that. Now, if you look here, what I've done, I've left beta unguided down here, right? I've taken beta z to the other side, it's plus beta z squared, then I take the square root of what's remaining here. Beta x was equal to m pi over a squared. Beta y squared was n pi over b squared, so now I'm down to this. And that's beta z, and that's exactly right. You with me on this? Mm-hmm. This is perfect. Everything over here depends on the frequency or on the value of m or n or a. In other words, it doesn't depend on some unknown. All this is known. You normally excite a waveguide at a known frequency, you know how big it is. And if you assume it's filled with air, then mu epsilon is 1 over c squared. But y'all with me on this? Here's the next step of this mystery. Let's do it here. Now what we end up doing is we take a look at what's called cutoff. So write this down. Make sure you put this down. We want to find out where the cutoff frequency is. And what this is like the frequency at which you can't go any lower and have information propagate. You can't have wave phenomena propagate. Consider it the low frequency, the lowest frequency the waveguide can work in. And it is a function of the mode numbers, the m and n, but I'm just telling you, it's the lowest frequency that will allow anything to transmit. Below this frequency, at least in the mode given. So how do we find the cutoff frequency? Well, this is how we find the cutoff frequency. All right, we let beta z go to 0. Now, when I say beta z, what did that have to do with? Think about the solution. See this e to the minus j beta z times z? If beta z goes to 0, right, there is no variation in z. Nothing is propagating. And remember, if you think about beta, and I don't want to spend too much time on this right now, beta is really, what is it? It's radians per meter. If your wave changes 0 radians per meter, basically the wave is bouncing up and down. It's not moving this way, all right? That's what it means. There's no z movement. It's only bouncing between, it's a capacitor effect, basically. A weird looking one, but that's it. All right, so when beta z equals 0, right, we call this the cutoff frequency. So this occurs at the omega cutoff frequency or at 2 pi the f cutoff frequency. Now just watch what I'm going to do. This beta z equals 0 means that, I'll try to do it over here. If I take this and make it 0, there's no propagation. Then I have this equation. So then I have beta cutoff here. This is beta unguided cutoff, really, right? Would be equal to, just watch this. This comes to the other side. It becomes a minus beta squared multiplied by minus. Finally, it would be the square root of m pi over a squared plus n pi over b squared. Try to follow me what I've done here. I've taken this equation, got rid of beta z because I'm looking for the cutoff frequency. That's what beta unguided is, right? The cutoff. And beta unguided is equal to omega cutoff, the cutoff frequency, and omega times the square root of mu epsilon is equal to this mess. I'm going to do one thing here. So it's beta unguided right there is equal to omega squared mu epsilon right there. I'm going to pull the pi out. I got a pi squared in both of these. Take a square root. I get a pi outside. And then I get m over a squared plus n over b squared. Square root of that is equal to this. Are you with me with what I'm doing so far? Now what I'm going to do is this. I'm going to replace omega cutoff with 2 pi f cutoff. With me? Because 2 pi, radiant frequency is 2 pi times frequency in hertz. And when I do that, I'm also going to divide both sides by the square root of mu epsilon. So now I have 2 pi f cutoff. That's what I'm after. Are you with me? Mm-hmm. Now you see the pi's cancel, right? And that's the reason I broke that pi out. So now the pi's cancel. And also I divide by 2. So I have 1 over 2, and this is FC, and this becomes critical. This is real, real important. That's the cutoff frequency of the waveguide. Now you're going to see this in a bit, but you can have different modes. For TM, the lowest possible mode that will propagate would be m equals 1. M and n are called mode numbers, and n equals 1. Here's why. If m was 0, the sign of 0 times, well, 0 times anything is still 0. The sign of 0 is 0. That means you have nothing. So m can't be 1, and n can't be 1. The lowest possible combination of m and m are m1, n1. That's called the TM11 mode, is the lowest possible mode. Lowest possible mode. Tell you what, I'm going to give you a quiz now. I'll pick this up on Wednesday. We don't have class, but because the next steps I'm going to go are going to be very, in my opinion, interesting, but I want to do a good job on them.